So far, we know that SN1 is a stepwise process. Rate of SN1 reaction depends on concentration of one compound, only concentration of substrate, for example, alkyl halide. Rate determining step of SN1 reaction is carbocation formation. So the step that carbocation forms is the slowest step, and it is the rate determining step for SN1 reaction. In the following animation, you will see the SN1 reaction between tertiary-butyl bromide, which is a tertiary substrate, and a nucleophile. This is a tertiary substrate because alpha carbon which is bonded to the leaving group, to the bromine, is bonded to 3 other carbons. 1, 2, and 3. So alpha carbon is bonded to 3 alkyl groups, which means this alpha carbon is tertiary and this substrate is a tertiary substrate. We know that tertiary substrates are not reactive in SN2 reactions because in SN2 reaction, nucleophile has to reach the alpha carbon, and in tertiary substrate, there are 3 bulky groups, 3 alkyl groups bonded to the alpha carbon. So alpha carbon is very crowded and nucleophile cannot reach the alpha carbon. Now let's check the mechanism of SN1 reaction for tertiary-butyl bromide. This is tertiary-butyl bromide. The yellow atom is bromine. So nucleophile cannot really get close to the alpha carbon because of all those alkyl groups. So instead of SN2 reaction, SN1 reaction happens. Leaving group, bromine starts to leave. So bond between alpha carbon and bromine breaks and a carbocation forms. This step that carbocation forms has the largest activation energy, and it is the rate determining step because we know that in stepwise reactions, the slowest step, the step with largest activation energy, is the rate determining step. So here in SN1 reaction, rate determining step is the carbocation formation step. And then nucleophile can attack the carbocation. Carbocation is planar and nucleophile can attack from either side. And the next step that nucleophile attacks the carbocation has a much lower activation energy and it's faster than the previous step. Okay, and then we have the product. Same reaction, this time faster. Leaving group leave, it starts to leave. Leaving group completely leaves, carbocation forms. Carbocation is planar, nucleophile can form a bond with carbocation from either side. It can attack from the front or from the back. And we get the products. In the video clip, a nucleophile was hydroxide, but by the end of the chapter, you will know that hydroxide is not a good choice of nucleophile for SN1 reaction. And I will explain it later at the end of the chapter. So in this reaction, it's much better if we use H2O as a nucleophile instead of hydroxide. Okay, so in SN1 reaction, the first step, leaving group leaves and a carbocation forms. And carbocation is planar and nucleophile can attack from either side. But remember, whenever there is a carbocation, you have to check the possibility of carbocation rearrangement. Okay, so check the hydride, possible hydride shift and metal shifts. If hydride shift or metal shift results in a more stable carbocation, that carbocation will undergo rearrangement. And we will get back to this later in this chapter. Okay, so this is the rate determining step. Carbocation formation is the rate determining step, and then nucleophile attacks. It can attack from either side, and we get the product. Now, what is the order of reactivity for different substrates? What is the effect of substrate on rate of SN1 reaction? We know that rate determining step is carbocation formation. So any substrate that gives a more stable carbocation will have a smaller activation energy and undergoes SN1 faster. So remember, we have tertiary, secondary, and primary substrate. Like this is a tertiary substrate, secondary substrate, and primary substrate. For tertiary, leaving group leaves, and a tertiary carbocation forms. For secondary substrate, leaving group leaves, and a secondary carbocation forms. In primary substrate, leaving group leaves, and a primary carbocation will form. We know that tertiary carbocation is more stable than secondary carbocation, and secondary carbocation is more stable than primary carbocations, which means tertiary carbocation forms faster. And tertiary substrate reacts faster in SN1 reaction. So the most reactive substrate in SN1 reaction is tertiary, then secondary, and then primary, and metal is the least reactive one. The reason is that rate determining step of SN1 reaction is carbocation formation, and tertiary substrate gives a tertiary carbocation, and tertiary carbocation is more stable than secondary, and primary forms faster. And this is the order of reactivity for different substrates in SN1 reaction. So any substrate that gives a more stable carbocation reacts faster in SN1 reaction. For each pair, which compound undergoes SN1 reaction faster? We know that tertiary substrates undergo SN1 fastest, and then secondary, and then primary, and methyl is the slowest one. Okay, here in A, we have a secondary substrate because the alpha carbon is bonded to two other carbons. Alpha carbon is bonded to two alkyl groups and one hydrogen. And the second one is a primary substrate because alpha carbon is bonded to only one other carbon and two hydrogens. And we know that secondary substrates undergo SN1 faster because secondary substrates gives a secondary carbocation, which is more stable than primary carbocation. In B, again, we have a secondary substrate. Alpha carbon is bonded to two other carbons and a hydrogen. And the other one is primary because alpha carbon is bonded to only one other carbon and two hydrogens. So remember that this whole group is one alkyl group. Okay? Now, again, we know that secondary substrate gives a secondary carbocation, primary substrate gives a primary carbocation, and secondary carbocation is more stable than primary, which means this secondary substrate undergoes SN1 faster. In C, the first substrate is tertiary because alpha carbon is bonded to 1, 2, and 3 other carbons. Alpha carbon is bonded to 3 alkyl groups. And the second compound is secondary because alpha carbon is bonded to 1 and 2 other carbons and one hydrogen. Alpha carbon is bonded to 2 alkyl groups. And we know that tertiary substrates undergo SN1 reaction faster because they give a more stable carbocation. For each pair, which compound undergoes SN1 reaction faster? In A, here we have a tertiary substrate because alpha carbon is bonded to 1, 2, and 3 other carbons, which means alpha carbon is bonded to 3 alkyl groups. And second one is also tertiary because alpha carbon is bonded to 1, 2, and 3 other carbons, which means alpha carbon is bonded to 3 alkyl groups. They are both tertiary substrates. So which one undergoes SN1 faster? Let's take a look at the carbocations. So when leaving group leaves, bromine leaves, and this carbocation forms tertiary. The second one, bromine leaves, again a tertiary carbocation forms, but the second tertiary carbocation, this one, is tertiary with resonance. And we know that tertiary with resonance is more stable than the tertiary carbocation without resonance. So this one is more stable because it is a tertiary carbocation with resonance. And this compound will undergo SN1 reaction faster because it gives a more stable carbocation. For B, both substrates are secondary because alpha carbon is bonded to 2 other carbons. It's bonded to 2 alkyl groups. Same here. Alpha carbon is bonded to two other carbons. And so which one undergoes SN1 reaction, or maybe they both undergo the SN1 reaction with the same speed. Let's check the carbocations. So bromide leaves, this carbocation forms, it's a secondary. Again, bromide leaves, and this secondary carbocation forms. But this one is secondary with resonance. And we know that resonance makes the carbocation more stable. More stable carbocation, faster SN2. So this one undergoes SN1 reaction faster. Okay, when you're comparing different compounds for SN1 reaction, always check the carbocations and see which carbocation, which one gives you a more stable carbocation. The one that gives a more stable carbocation undergoes SN1 reaction faster. Similar to SN2 reaction, a better leaving group makes the SN1 reaction faster. Between these two compounds, the second one, the one with iodine, undergoes SN1 faster. They're both secondary. They both give the same carbocation, the secondary carbocation. But the second one has a better leaving group. Iodine is a better leaving group than bromine, so it can move faster, and that makes the SN1 reaction faster. SN1 reaction is more sensitive to quality of leaving group than SN2, because in SN2, nucleophile will attack first and it will push out the leaving group. So somehow it helps the leaving group to leave. It is pushing out the leaving group. But in SN1 reaction, leaving group doesn't have that help. So leaving group, quality of leaving group is important in both SN1 and SN2, but it is more important in SN1 reaction. Now let's check stereochemistry of SN1. Remember, in SN2 reaction proceeds with inversion of configuration because nucleophile attacks from the backside, which results in inversion of configuration. In SN1 reaction, leaving group leaves first, and a carbocation forms. And we know that carbocation is planar. A nucleophile can attack from either side, so from front or from back, and gives a mixture of both enantiomers. So if we start with R at the end, we get a mixture of R and S. Same if we start with S at the end, we get mixture of R and S. We get a racemic mixture, which means SN1 reaction proceeds with both retention and inversion of configuration. Inversion of configuration means that configuration of the chiral center will change at the end of the reaction. For example, R becomes S, S becomes R, and retention of configuration means that configuration of the chiral center will not change at the end of the reaction. R stays R, S stays S. And in SN1 reaction, both inversion and retention of configuration will happen because carbocation is planar and nucleophile can attack from the front or it can attack from the back side. These images show how inversion and retention of configuration happen. So here we have carbocation is planar, so chloride can attack from front or it can attack from the back side. In the second image, so leaving group leaves and carbocation forms. Carbocation is planar and nucleophile can attack from either side. If it attacks from the back side, inversion of configuration happens. So for example, if we start with, if the substrate is S, configuration of chiral carbon in alpha carbon is S, and nucleophile attacks from the backside to the carbocation, inversion of configuration and configuration of chiral carbon will be usually R. And if the nucleophile attacks from the front side, configuration of chiral carbon, configuration of the alpha carbon will be S in the product, similar to the substrate. Okay, and usually there will be more inversion of configuration than retention of configuration, as you can see. And the reason is that when leaving group leaves, it is still around, it is close to carbon with positive charge because they are an ion pair. So it's harder for nucleophile to attack from the front side than back side. That's why retention of configuration is usually less than inversion of configuration. But we get a mixture at the end in SN1 reaction. So stereochemistry of SN2. SN2 proceeds with inversion of configuration. SN1 proceeds with both inversion and retention of configuration because a carbocation forms in SN1 and carbocation is planar, so nucleophile can attack from either side. From back side, inversion of configuration. From the front side, retention of configuration. Okay. Since intermediate of SN1 reaction is a carbocation, rearrangements can happen in SN1 reactions. For example, here we have a secondary substrate here because alpha carbon is bonded to two other carbons. Alpha carbon is bonded to two alkyl groups. In SN1 reaction, we know that leaving group leaves and a carbocation forms. So first, the secondary substrate becomes a secondary carbocation. A nucleophile can attack this secondary carbocation. But whenever there is a carbocation, we have to check the possibility of rearrangement. And here, so you have to check the hydride shift and metal shift from adjacent carbons. And the metal shift from this adjacent carbon converts the secondary carbocation to a tertiary carbocation, which is more stable. So after a metal shift, secondary carbocation becomes tertiary. So there will be a mixture of secondary and tertiary carbocation in this reaction, and since tertiary is more stable, there will be more tertiary carbocation, and two products are possible. Nucleophile can attack the secondary carbocation, and this product will form or it can attack the tertiary carbocation, and this product will form. Okay, so we get a mixture of these two products, but the one that comes from tertiary carbocation is the major product. There will be more of this one. The reason is that tertiary is more stable than secondary, and there will be more tertiary carbocation than secondary carbocation.